April 8, 1941. At exactly 2:35 in the afternoon, a massive aircraft rolled down the runway at Nakajima's test facility outside Tokyo. It was enormous, more than 100 feet long, a wingspan stretching nearly 140 feet from tip to tip. 4 engines roared as the aircraft gathered speed, the sound echoing across the field. Engineers from the Imperial Japanese Navy stood watching in silence. 18 months of work were riding on what happened next. The aircraft lifted into the humid spring air. At first, there was relief, then concern. The climb was slow, too slow. The engines strained, pushed hard against a weight they seemed barely able to carry. Inside the cockpit, the controls felt heavy, sluggish, unresponsive. The pilots exchanged quick glances, their hands tightening on the throttles. Something was wrong. This was meant to be Japan's first true 4-engine land-based bomber, an aircraft designed to carry the war across the Pacific, to reach farther than any Japanese bomber ever had before. Instead, on its very first flight, it was already revealing a deeper truth. This aircraft did not fail by accident. It had been broken long before it ever left the ground. 6 years earlier, the story began far from Japan, not with war, but with ambition. In the mid-1930s, American commercial aviation was entering its golden age. Airlines were no longer fighting simply to survive. They were competing for prestige, for distance, for the future itself. Passengers wanted more than short hops between cities. They wanted to cross a continent, overnight, in comfort, above storms and weather that had grounded earlier generations of aircraft. At the center of that vision stood United Airlines. Its president, William Patterson, believed the next leap in aviation would not come from the military, but from civilian travel. He imagined an aircraft so advanced it would make every existing airliner obsolete the moment it entered service. It would have 4 engines. It would fly non-stop from coast to coast. It would carry more than 40 passengers in daylight, or sleeper berths at night. It would offer air conditioning, unheard of comfort, and eventually even cabin pressurization. No airline had ever operated a 4-engine landplane in scheduled passenger service. The risks were enormous, the costs were staggering, but the reward was absolute dominance of the skies. Patterson took his vision to the Douglas Aircraft Company. Douglas had just revolutionized aviation with the DC-3, an aircraft so successful it redefined air travel worldwide. Its designers knew better than anyone how fragile progress could be. Bigger did not automatically mean better. Complexity could destroy reliability. Still, the challenge was irresistible. Douglas agreed to consider the project, but only if other airlines were willing to share the risk. They were. American Airlines joined, Eastern Airlines followed, Pan American and Transcontinental and Western Air soon committed as well. Together, 5 airlines pooled $500,000 to fund what would become the most ambitious commercial aircraft ever attempted. On paper, it was the future. In reality, it was a warning, because every promise the aircraft made, greater range, greater comfort, greater capability, demanded weight. Systems, power, reinforcement, and weight once added is never easily removed. Douglas assembled one of the most experienced engineering teams in American aviation. At its head was Arthur Raymond, the man who had guided the DC-3 from drawing board to triumph. If anyone understood how to turn ambition into a working airplane, it was him. But this time, nothing was familiar. The aircraft they were being asked to build was larger, heavier, and more complex than anything that had ever carried paying passengers. Every major system posed a question no one had answered before. How do you build a wing strong enough to carry 4 large engines, yet light enough to fly efficiently? How do you design landing gear that can absorb the weight of a 60,000-pound aircraft, again and again, day after day? How do you route fuel lines, electrical wiring, and hydraulic systems through a fuselage that must also be quiet, comfortable, and safe? The problems multiplied as the design took shape. The cabin was designed to be wider than any airliner before it. That meant a larger fuselage. A larger fuselage meant more structural reinforcement. More reinforcement meant more weight. Power-assisted controls were added to help pilots handle the enormous control forces. That meant motors, linkages, and backup systems, all of them heavy. Electrical demand soared. Air conditioning, lighting, navigation equipment, and auxiliary power systems all had to function reliably at altitude. The aircraft would use alternating current, advanced for its time, and far more complex to maintain. Even the tail presented a dilemma. A single vertical stabilizer large enough to control the aircraft would make it too tall for existing airport hangars. Airlines could not afford to rebuild their infrastructure for one airplane. So Douglas chose a compromise, a distinctive triple-tail design, lower in height, but mechanically more complex. Every decision solved one problem and quietly created another. To make sure the aircraft would even fly, Douglas built a detailed wind tunnel model and subjected it to hundreds of hours of testing. Engineers analyzed airflow, stability, and control response at speeds and altitudes commercial aircraft had never reached before. By the time the prototype took shape, the numbers were staggering. Over 8,000 individual drawings, more than 1 million rivets, hundreds of thousands of man-hours. What emerged from the factory was called the DC-4E. It looked like the future, but buried inside its gleaming aluminum skin was a truth no one wanted to face. This aircraft was already carrying the weight of every compromise that had created it. On June 7, 1938, the DC-4E was ready to fly. The setting was Clover Field in Santa Monica, California, the heart of Douglas Aircraft's operations. Years of design work, testing, and quiet anxiety had led to this moment. At the controls sat Carl Cover, Douglas's chief test pilot. Cover was no stranger to first flights. He had flown the DC-1, the DC-2, and the DC-3 on their maiden journeys. Few men alive understood the difference between a promising airplane and a dangerous one as well as he did. One by one, the 4 Pratt & Whitney twin Hornet engines came to life, their deep radial rumble filling the air. Ground crews stepped back. The aircraft began to roll. The DC-4E used more runway than any Douglas airplane before it. Slowly, deliberately, it gathered speed. At the calculated airspeed, Cover eased back on the controls. The aircraft lifted off. For 45 minutes, the most advanced airliner in the world flew over Southern California. There were no dramatic failures, no emergencies. When Cover landed, the relief among the engineers was palpable. But relief was not the same as confidence. Cover's report was careful. The aircraft flew, but it felt heavy. Control forces were high, even with power assistance. Response was slower than expected. Nothing was unsafe, but nothing felt effortless either. Test flights continued through the summer and into the fall. Engineers explored climb performance, stability, and handling across the envelope. As fuel loads increased and simulated passenger weight was added, the margins began to narrow. The DC-4E was flying, but it was doing so with little room to spare. Certification took longer than expected. Problems appeared, were corrected, and replaced by new ones. Systems interfered with one another in ways that had not appeared on paper. Complexity revealed its cost. Finally, in May 1939, the aircraft was approved for limited commercial evaluation. United Airlines took delivery of the prototype. This was the moment the engineers could no longer protect it. Because test pilots fly airplanes with patience and sympathy, airlines fly them to schedules, and schedules have no tolerance for weakness. United Airlines put the DC-4E to work the way it intended to operate every airplane in its fleet. Not gently, not cautiously, but as a machine expected to perform day after day, on time. Almost immediately, problems surfaced. The aircraft demanded constant attention from ground crews. Mechanics trained on the dependable DC-3 found themselves overwhelmed by systems they had never worked with before. Electrical circuits were complex and unfamiliar. Hydraulic systems required careful calibration. Minor faults cascaded into delays. Every hour the aircraft spent on the ground cost money. Fuel consumption proved even more alarming. The 4 twin Hornet engines drank fuel at a rate far higher than Douglas had predicted. Range figures that looked acceptable on paper collapsed in real-world operation. Flights that were supposed to span the continent now required compromises, reduced payloads, intermediate stops, or both. To make the aircraft economically viable, United pushed seating capacity beyond the original design. Passenger count increased, gross weight climbed. The DC-4E now weighed nearly 65,000 pounds. The engines, designed for a much lighter airplane, struggled. Climb performance deteriorated. Cruise speed lagged behind expectations. Margins vanished. Pilots reported that the aircraft felt sluggish, particularly during takeoff and climb, the most dangerous phases of flight. In bad weather or high temperatures, performance degraded even further. None of these issues alone doomed the aircraft. Together, they did. Airline executives were forced to confront an uncomfortable truth. The DC-4E was not unsafe. It was not poorly built, but it was too complex, too heavy, and too expensive for practical airline service. Pan American and Transcontinental and Western Air had already withdrawn from the program, choosing a smaller, more conservative aircraft instead. Now, United, American, and Eastern reached the same conclusion. The future they had funded did not work. Douglas was left with an airplane no one wanted. They had invested millions of dollars, years of effort, and their reputation into a machine that had reached the limits of what civilian aviation could tolerate. The DC-4E did not fail in flight. It failed in service, where reality cannot be negotiated. For Douglas, the failure of the DC-4E was more than an embarrassment. It was a financial wound. The company had invested millions of dollars of its own money into an aircraft that had no buyers. The prototype sat at the factory, too valuable to scrap, too flawed to sell to any American airline. Something had to be done. The first decision was internal. Douglas would not abandon the idea of a four-engine transport. Instead, the engineers would start again, applying every painful lesson the DC-4E had taught them. The next aircraft would be simpler, lighter, more practical. Complex systems would be stripped out. Weight would be reduced wherever possible. Reliability, not ambition, would guide every choice. But that solution would take time. The DC-4E still remained, unwanted, expensive, and quietly draining resources. Then, in late 1939, an unexpected inquiry arrived. Representatives from Mitsui Trading Company approached Douglas with an offer. They were acting on behalf of Japan Airlines, known domestically as Dai Nippon Koku. The airline was expanding rapidly as Japan's influence spread across Asia, and it needed long-range aircraft to serve distant routes. The DC-4E, despite its problems in American service, was far more advanced than anything flying in Japan. Mitsui offered $950,000. For Douglas, the decision seemed straightforward. Selling a civilian aircraft to a foreign airline was legal. American manufacturers did it regularly. There were no export restrictions on commercial airliners. The offer would recover a significant portion of the losses. Douglas accepted. What they did not know, what the American government did not know, was that Japan Airlines was not the true customer. The real buyer was the Imperial Japanese Navy. To them, the DC-4E was not a failed airliner. It was a shortcut. A chance to acquire four-engine technology they did not yet possess without enduring the years of trial, error, and failure that Douglas had already survived. The aircraft that American Airlines had rejected was about to begin a second life, one its designers had never intended. In September 1939, the DC-4E left the United States in pieces. At the Douglas factory in Long Beach, workers carefully disassembled the aircraft. Wings, fuselage sections, engines, and systems were packed into crates and loaded onto a freighter bound for Japan. Along with the metal came something even more valuable. Every drawing, every test result, every maintenance manual, even the wind tunnel model used to refine the design. Douglas treated the shipment like any other customer delivery. A team of American technicians followed the aircraft across the Pacific to assist with reassembly. When the DC-4E emerged from its crates at Haneda Airport near Tokyo, it instantly became the largest and most advanced aircraft in the country. It wore the green and silver livery of Japan Airlines. Newspapers photographed it, executives posed beside it. The aircraft was presented as a symbol of modern Japan. Then, almost as suddenly as it appeared, it was gone. Japanese newspapers reported that the DC-4E had crashed into Tokyo Bay shortly after takeoff. The loss was total, they said. Nothing could be recovered. There would be no further explanation. The story was a lie. The aircraft had not crashed. It had been quietly transferred to Nakajima Aircraft Company under direct orders from the Imperial Japanese Navy. Inside a guarded hangar, the DC-4E was stripped down piece by piece. Engineers measured every structural member. They traced wiring harnesses and fuel lines. They weighed components and photographed assemblies from every angle. The airplane was reverse-engineered in silence. The fake crash served its purpose. It explained the aircraft's disappearance. It discouraged foreign questions. And it concealed a secret program that Japan hoped would reshape the balance of air power. The DC-4E had crossed the ocean as a civilian airliner. It had vanished and been reborn as a weapon. Inside Nakajima's hangars, the DC-4E ceased to exist as an airplane. What remained was a reference. Japanese engineers studied the aircraft with intense focus. This was the most complex machine they had ever examined. Nothing of comparable size or sophistication had ever been built in Japan. The wing was copied almost exactly. Its structure, its thickness, even the outward angle of the engines were preserved. The tricycle landing gear, rare and advanced by Japanese standards, was adopted without hesitation. But the fuselage had to change. Where passengers once sat in upholstered seats, Nakajima engineers carved out a long internal bomb bay. The nose was reshaped into a glazed bombardier station. Defensive gun positions sprouted along the spine, the tail, and the belly of the aircraft. Armor was added, weapons were added, crew stations multiplied, and with each addition, weight accumulated. The elegant balance Douglas engineers had struggled to control tipped further and further away from equilibrium. For propulsion, Nakajima chose its own engine, the NK-7A Mammary. On paper, it was powerful, more powerful than the American engines the DC-4E had used. In theory, it would solve the aircraft's performance problems. In practice, it created new ones. The Mammary was ambitious, complex, and still immature. Cooling problems emerged almost immediately. Reliability was poor. Power output rarely matched specifications. Still, the Japanese Navy pressed forward. The aircraft was designated the G5N. It was given the name Shinzan, Deep Mountain. The name was meant to convey strength, permanence, an unmovable presence in the sky. In early 1941, the first prototype rolled out onto the runway. It dwarfed every other aircraft Japan had built. Navy officers watched with pride as Japan entered what they believed was the era of four-engine strategic aviation. When the Shinzan lifted into the air on April 8, 1941, it fulfilled a long-held dream. But the dream did not survive the flight. The aircraft climbed slowly. Control response was heavy. The engines ran hot and uneven. Pilots reported that the Shinzan felt less like a purpose-built bomber and more like exactly what it was: a civilian airliner forced into a role it had never been designed to play. Flight testing quickly stripped away the remaining illusions. The Shinzan was simply too heavy. Even at reduced loads, the aircraft struggled to climb. Pilots reported long, vulnerable ascents that left the bomber exposed to interception for minutes at a time. At altitude, performance failed to improve. Maximum speed fell well below expectations. In level flight, the Shinzan was slower than many enemy fighters. Even worse, it was slower than the American B-17 bomber it was meant to rival. Service ceiling was limited. The aircraft could not climb high enough to escape anti-aircraft fire or modern interceptors. Its defensive guns, impressive on paper, could not compensate for a lack of speed and altitude. Range, the very reason the aircraft existed, also fell short. Fully loaded, the Shinzan could not meet the Navy's minimum requirement. It could reach nearby bases, but the dream of striking far-off targets across the Pacific evaporated. The bomber designed to project power instead revealed its limitations with every flight. Nakajima engineers tried to fix what could not be fixed. They modified engine cowlings to improve cooling. They adjusted propeller pitch. They refined fuel systems and reduced power settings to improve reliability. Nothing changed the fundamentals. Pushing the Mammary engines harder caused failures. Detuning them to keep them alive robbed the aircraft of what little performance it had. The Shinzan was trapped in a vicious cycle. Power destroyed reliability, reliability destroyed performance. In desperation, Nakajima built new variants using different engines. Mitsubishi power plants replaced the Mammary in hopes of salvaging the design. The aircraft became safer to fly. It also became even slower. By 1942, the verdict was unavoidable. Japan's first four-engine bomber could not bomb. The aircraft that was supposed to carry the war across oceans could barely carry itself. What Nakajima had built was not a strategic weapon, but an object lesson in the dangers of copying what you do not fully understand. The Imperial Japanese Navy could not ignore reality forever. By late 1942, the Shinzan's fate was sealed. No amount of refinement could transform it into the long-range strategic bomber the Navy had envisioned. The aircraft was formally removed from combat consideration. But Japan could not afford to waste machines of this size. 4 of the 6 prototypes were stripped of their bomb racks and most of their defensive armament. Armor was removed. Crew requirements were reduced. The aircraft were redesignated as long-range transports. The Shinzan became the Shinzan Kai, modified deep mountain. Instead of bombs, it now carried cargo, spare parts, medical supplies, personnel. It flew supply routes across the Japanese Empire, linking distant island bases that smaller aircraft could not reach. The aircraft meant to threaten American cities now hauled freight. Allied intelligence eventually spotted the large 4-engine machines in aerial photographs. Analysts classified them as heavy bombers and assigned them the codename Liz. Plans were quietly drafted to counter a threat that no longer truly existed. The irony was complete. The aircraft Japan had hoped would project power instead consumed resources. It required maintenance, fuel, and protection, offering little in return. Its presence did not change the course of the air war. It did not force new Allied strategies. It simply moved supplies until it was worn out, destroyed, or scrapped. None of the Shinzan aircraft survived the war. They disappeared quietly, without victories, without legend. The bomber that was meant to alter history left barely a footprint at all. While the Shinzan faded into obscurity, the story of the DC-4 did not end in failure. At Douglas, the lessons of the DC-4E had been absorbed the hard way. Engineers returned to their drawings with humility. They understood now what had gone wrong, not in theory, but in practice. They knew which systems had added complexity without value, which features had promised too much, which compromises had quietly sabotaged performance. The next aircraft would carry the same name, but almost nothing else. The redesigned DC-4 abandoned the triple tail in favor of a single, simpler fin. Power-assisted controls were removed. Pressurization was delayed. Systems were simplified. Weight was cut relentlessly. Most importantly, the aircraft was designed not to impress, but to work. When war came, that design proved invaluable. The U.S. military adopted the new DC-4 as the C-54 Skymaster. More than 1,000 were built. They carried troops, cargo, and wounded soldiers across oceans. They sustained entire campaigns through airlift alone. President Franklin Roosevelt flew in one. After the war, the same aircraft fed a starving city during the Berlin airlift, landing every few minutes with coal and supplies. The irony was complete. The design that failed became the foundation of one of the most successful transport aircraft in history, because its creators understood why it had failed. Japan never had that chance. Nakajima received the aircraft's shape, its measurements, its metal, but not the invisible knowledge behind it. They could see what Douglas had built. They could not see the years of debate, the dead ends, the rejected alternatives. They copied the artifact. Douglas learned from the process. Technology, the Shinzan proved, cannot be stolen whole. In the end, Japan spent nearly $1 million, years of effort, and enormous industrial resources to build a bomber that never bombed. Douglas turned the same failure into success. The deep mountain cast no shadow across the Pacific, but the lesson it left behind still stands.